This is a shallow tank with some water inside. A tank with a large surface area. Suppose that I drop a stone. Right, let's say I drop a stone into the water. So the stone plunges into the water and it sets off ripples that start traveling out from this little stone that I dropped into the water. These are lots of ripples spreading outwards. And we call this a ripple tank. The purpose of this tank is to allow us to see and observe how waves behave in different situations. So this is one of the simplest situations where we just drop a stone inside. Now, let me just think a little bit about, say, the waves produced by the stone. That means these ripples. Let me think about it in relation to the waves along a string that I have been talking about. Now, they don't look exactly the same, right? If you have a wave along a string, it sort of goes up, down along the string. But if you have a ripple, it comes out in circle, and the circles gets bigger and bigger. But we can imagine that along the surface, there would be, if we move along a certain line on the surface, we would see the surface going up and down. Okay, and that would look more like what we have seen on the string. Like if I move, say, along a straight line from the stone, then I might imagine that the surface of the water along this line would be doing this. It would be going up, down, up, down, up, down. Okay, if you look at it at a low angle, you'll find that the surface is actually going up and down. So if you think about it, look at it this way, it would look like a string, a wave traveling along the string, except that instead of just wave traveling along one line, we have waves going out in all directions. We have waves in that direction, we have waves going out in this direction, waves going out in this direction. So waves going out in all directions. But the interesting thing, the thing that is different from just waves along a string is that if you look at it from the top, you see an area. You don't just see a single direction. You see a whole area of wave spreading out. So this is one simple situation that we would be familiar with if you have ever dropped a stone into a pond or a river of water, puddle of water. So let me now look at another situation. Suppose that I take a long ruler. Okay, a short ruler, doesn't matter. Suppose that I have a short ruler somewhere down here, and suppose that I move this ruler up and down. Okay, so I push this ruler into the water and out again. So I keep pushing it up and down. Maybe I can have a motor that does this automatically, or I can do it with my hand. But in any case, by pushing this long piece of ruler or piece of wood in and out of the water, it will generate a wave. And the wave would, instead of the wave, the ripple from a stone that looks circular and spreads out, because I have a long ruler, it will generate a wave that looks with wave fronts that look like a straight line. Alright, so I'll get wave that looks like straight lines traveling out. So traveling outwards. So along a particular line here, I would expect to see that the surface of the water will be going up and down. So, for example, this will be up, down, up, down, up, down, up, down. If I follow, say, that line, it will go up, down, up, down, up, down, up, down, up, down. That line there, up, down, up, down, up, down, down, up, down, and so on. Right, so I have these waves, and the interesting thing here is that the wave along all these lines, all right, are such that their peaks are all can all be joined up together to form straight lines, right? Like this set of peaks form a straight line. The next set of peaks we can also join up to form a straight line. So which is why we can see ripples, which is why we can see waves like that looks like lines traveling outwards. Okay, and these lines that we can actually see, at least those the part that is close to the peaks, right? We can actually see the reflection of light from this. These lines are called, they actually have a name, they are called wave fronts. They're called wave fronts. They are also called phase fronts. I haven't talked about phase yet. I'll say more about that later. So this is what we would expect. Okay. Let me now think of another situation. I still have my ruler that I'm pushing in and out the water to create this wave. Now what I'm going to do now is I'm going to add say two pieces of maybe plastic or wood along here. One piece here and another piece here. Alright, so just two pieces of solid that I place down here. Now the purpose of this is to block the wave, or some parts of the wave, except for this gap here. So I have two pieces of solid here. Wave cannot go through these two bits. Okay, so this bits here, but wave can go through this gap here. So if I now look at what happens when I push the ruler in and out, the waves gets blocked here, but the part that can come through here, right, we can imagine what happened, and you can actually try it out on some water if you like. You'll see that the wave that comes through here, it would actually start spreading to both sides. Right, it will start spreading out to the two sides. And you would most likely not find the wave going straight ahead. Right, it will almost definitely spread out. That's not surprising. I mean, if you drop a stone in the water, after all, if you drop a stone into this tank of water, you get ripples that are circular and spread out. So if you have a small gap there with wave coming through, then it's not surprising that it would actually spread out quite a bit. Now, but let's think about this in another way. Think about this. Think about let's say following the direction of this wave. So starting from here, as you move this long piece of ruler up in and out of the water, it generates this wave. Now, if I follow, say, a particular point on this wavefront or on this peak, right, it will be traveling outwards. Okay, it will be traveling outwards. So the wavefront will be traveling outwards. Now, but when it reaches here, because it spreads out to both sides, what would happen is that we might imagine that the wave, the direction of the say the peak of a wave that we are following would bend, would change direction. Okay, it would change direction. So in that sense, the wave bends. Right? The wave bends to one side. Now, if I follow it from closer to the other side of the gap, okay, if I follow the peak as it moves, travel outwards. So this peak is not stationary. It's like a ripple. It actually this line that you see here, it would actually be moving outwards. So the whole all these lines will be traveling outwards like ripples, right? Except that they look straight instead of the circular ripples. So this, if I follow a particular point on the line, I'll find that as it comes out, it bends. So when a wave goes through a gap, it will bend, right? When it goes through a corner. And that's one of the features of waves. Waves can bend around corner. Okay. And in the middle, right, it will roughly maybe either bend to one side, or some of it might go straight, and then you have some of it going the other way. So it either bends one way or the other, or more or less goes straight if it's close to the middle. So this is what we would expect. Now this bending, this spreading out from a gap and bending around the edge has a name. And this name is called diffraction. Diffraction. Right, diffraction is the bending of a wave round a corner. That's one way to say it, or around an edge. Now let me change this situation slightly. Now what I'm going to do is I'm going to increase the gap. I'm going to increase the gap a little bit. Okay. So I'll still have a piece of solid here to block some part of the wave, but now I want a bigger gap. A bigger gap there. And what would happen when I push this ruler up and down and generate these waves? Okay, the wave would come through the gap. Okay, it will go through the gap. Now as it comes through the gap, it will spread out. But what you would find is that it would not spread out as much as before. It will spread out a little bit, but more of it would go straight or closer to straight. Okay, so it will spread out less when the gap is bigger. If we follow say a point on on the peak of the wave. As it comes through, it will bend a little bit, but not as much as when the gap was small. So for a big gap, there's less bending involved, and that's one of the property of diffraction. It diffracts more when the gap is small. Now it would diffract the most. All right, the most diffraction, the biggest amount of diffraction would happen if the gap is comparable to the wavelength. What do you mean by comparable to the wavelength? Okay, let's have a look. The wavelength would be the distance between the peaks. If you imagine that those lines represent the peaks of the wave, so the distance between peaks is the wavelength, lambda. Now, if the size of this gap is about the same as the wavelength, or comparable could be maybe 2 or 3 times, at most a few times of the wavelength, then the wave would bend a lot. It will spread out a lot more. But if the size of the gap is much bigger than the wavelength, much bigger, it could be maybe 10 times or more, or 100 times, then there would be less bending. So smaller gap, more bending; bigger gap, less bending. And that's one of the features of diffraction.